The point is I want to talk about sets and functions and make sure that you're good on set notation and function notation, because we're going to be using those in these upcoming sections starting in chapter 7 and then a lot more in chapter 8. Okay, before we get on to sets, we need to talk about types of numbers. Okay, these are just general types of numbers. This may be some new terminology for some of you. Integers. What an integer is, it's a whole number. It can be positive, it can be negative, or 0. So it goes all the way from negative infinity to, I'll just start writing it at -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, and so on forever in both directions. So your integers are positive, negative, and 0, whole numbers. Okay, your real numbers, those are similar to integers, except it also includes all the decimal numbers and fractions in between all of these integers. So your real numbers are really essentially any real number that you can think of. So it includes integers, fractions, decimals, positive numbers, negative numbers, everything. One way to think of this is to draw it on a number line. And actually the real numbers are the number line. So here's the number line from negative infinity to infinity. We'll put 0 in the middle there. 1, 2, 3, 4, and -1, -2, -3, -4, and so on. Okay, but your real numbers are anything on this number line. I'm going to color in the real numbers here in orange. Okay, and you're probably saying, well, why do we even discuss real numbers? Aren't all numbers real? And the answer is actually no. Some numbers are imaginary, and we will get into this a little bit in this course. These will come back later on. So imaginary numbers have an I in them. I is the imaginary number that equals the square root of -1. Now if you think about it, the square root of -1 does not exist because no number squared will ever be negative, because a positive number squared is a positive number and a negative number squared is a positive number. So this realistically does not exist. However, the interesting thing is it's used a lot in actually solving bigger equations. So what you'll find with the more math you take is that oftentimes there are questions that involve real numbers, but that require you to go through imaginary numbers to get to the real answer. So without imaginary numbers, you wouldn't be able to get to the answer, even though the answer is not imaginary. So they are very, very useful in solving equations with math. But anyways, anything that does not have an I is real. Anything with an I in it is imaginary. Okay, now let's talk about sets. Sets are just that, just a set or a collection of objects. That's what a set is. The objects in a set in math are often called elements. Okay, a finite set has a countable number of elements or a countable number of objects in it. For example, this down here, it says if a set has a finite number of objects in it, it can be described by listing all of its elements. So if it's got a countable number of elements in it, you could just list them all out. So for example, the set of striped billiard balls can be listed. Sets are typically listed in curly braces. So striped billiard balls. Let's see, they start at 9 and go up to 15. So there's the set of striped billiard balls. Okay, as opposed to an infinite set, which has an infinite number of elements in it. So for example, the set that we were just discussing, the set of real numbers, can't be listed because there's infinitely many real numbers. So instead what you could do is you could draw the set of real numbers on the number line, just as I did before, from negative infinity to infinity. Okay, so real numbers, if you have an infinite set, you cannot just list out all the elements because it's impossible, because there's an infinite number of things in it. So there are different ways to describe sets that have an infinite number of elements in them, which we'll learn coming up next. Okay, one way is with inequalities. Now this is not a formal way of describing an infinite set, but it does work. Okay, first we're going to draw the set of all real numbers that are either greater than 2 or less than or equal to -1 on a number line. So there's 0, 1, 2, and -1, -2, and so on. Okay, so if I want to draw the set of all real numbers, so all decimals, fractions, everything in between, all the integers, that are either greater than 2, okay, now it says greater than 2. It does not say greater than or equal to 2. So 2 is not included in this set. So I'm going to put an open circle at 2 because 2 is not included. However, everything bigger than 2 is. So all of these numbers are included in the set all the way up to infinity. Or if the number is less than or equal to -1. So -1 is included in this set, so we'll put a closed circle there to indicate that -1 is a part of it. And all the numbers less than -1 are part of the set. So the colored in area are represent all the numbers that are a part of this set. And now let's describe it with inequalities. So to use inequalities, we have to introduce a variable name. I'm just going to use x because that's what you're probably used to. So using inequalities, this would be the set of all x that is less than or equal to -1, or the set of x that is strictly greater than 2. So here it is on a number line and with the inequalities. Now, like I said, this isn't a formal way of writing or describing a set. We'll learn that next with set builder and interval notation, but it does do the job. It describes the set of numbers that you're discussing. Okay, let's do another one just for practice. Let's describe the set of all real numbers that are both greater than 2 and less than or equal to 5 on a number line. So this is a little different. The number has to be greater than 2 and less than 5. Now you don't have to put 0 in the middle of your number line. Because 0 is not a part of this set, I'm not going to. I'm going to put 0 over here. And you also don't have to label every single tick mark. You can just label the important ones like that. Okay, so we're looking at the set of real numbers that are both greater than 2, strictly greater than 2, and less than or equal to 5. So we include 5 but not 2, and all those numbers in between there are the numbers that we're discussing. Okay, so how would you write that in inequalities? Well, you could say x has to be greater than 2, and, that word and there is very important, x has to be, oops, that should say 2 there. X is greater than 2, and x has to be less than or equal to 5. Now there is a more compact way to write this inequality right here, which we're going to learn later on in the course. I don't want to confuse you for now, but if you know what I'm talking about, you can use that more compact notation. Okay, now let's look at some formal ways to write set notations. The first one is set builder notation, and it's just an extension of inequality notation, which is what we were using here and here. Okay, I want to describe the set of numbers greater than 3 or less than 1, greater than 3 or less than or equal to 1 in set builder notation. Okay, so that's the set of all numbers. Now we have to give it a variable name, just like we did up here. We called this x to describe the numbers. So I'm going to say it's the set of all numbers x. Then you put a long vertical bar, and that means such that, and I'll write that out in a moment, such that x is a real number and, let's see, x has to be greater than 3 or x has to be less than or equal to 1. So there is this in set builder notation. So the curly brackets are read the set of, the x is read all x, this long vertical bar, and sometimes you won't see a vertical bar, sometimes you'll see a colon instead. So if it's a vertical bar or a colon, that works. That's read such that, it's just a separator or shorthand notation really, such that, And then you describe the set. Now you can describe the set over here in words, you can list it out, you can use an inequality. It doesn't matter how you describe it, but all of this part is just a description of the set. Okay, so let's do another one for practice here with set builder notation. Okay, try this one on your own first. Make sure you're pausing the video as you go here. So let's describe the set of all positive integers less than 6 in set builder notation and on a number line. So actually, let's do the number line first. Positive integers. Okay, remember an integer is a whole number that's either positive, negative, or 0, but it does not include any of those fractions or decimals in between the whole numbers. So we're only talking about whole numbers less than 6, okay? Well, let's see, let's put 6 here. There's 0, and then it just keeps going in that direction. Whole numbers less than 6. Well, that actually technically does not include 6 because it does not say less than or equal to 6. But it does include 5, 4, 3, 2, 1, 0, and so on. All of these numbers. And then to indicate that you keep going, you can just draw on the arrow there to indicate you keep going on forever. And to make this more clear, I might even draw in a couple more here. Okay, so there it is drawn on the number line. Now this one's interesting and it cannot be described by inequalities because this inequality, unless you say it's a real number, that inequality implies that it is a real number. So what I'm saying is you cannot do this. This would be wrong. You cannot say the set of all x such that x is less than 6. Okay, that's wrong because that includes all those decimals and fractions less than 6. Because if you don't state what kind of number x is, then x is assumed to be a real number. So that includes decimals, etc. So the only way to technically write this is, well, 2 ways. One is to say the set of all x such that x is an integer and x is less than 6. Actually, there's several ways to write this. Write this would be to say the set of all x such that x is an integer. And you could also state that x is less than or equal to 5. That describes the exact same set, so either of those is technically correct. Or you could do this. You could say the set of all x such that x is equal to, and then you just list them out and establish a pattern. Now you can't list all of them out because there's an infinite number of integers that are less than 6. But what you can do is list enough to establish the pattern. So you can say 6, 5, 4, 3, and I'm going to go on to the negatives to establish that negative numbers are included, and then you put a little ellipsis there, and that implies that it goes on forever into that direction. So there's often more than one right way to describe a set. All of these 3 notations work. Now another thing that would work is you could use a different variable. Nothing in here says you have to call it x. So you could have called this y. You could put y here and y there. You could have called it w. It doesn't matter what you call it as long as you're consistent in using the same variable each time. Okay. Next, let's talk about interval notation. It's used to describe sets similar to these we just described in set builder notation. It's just a shorter way of writing it. So what an interval is, it's a continuous set of real numbers between either 2 numbers or infinity. So that includes all decimals and fractions and etc. because it's real numbers, an interval notation does. So an interval notation cannot be used to describe something like this previous example because it involved integers, not real numbers. So interval notation only works with real numbers. In interval notation, if you have brackets, those are used to include the endpoints, and if you have parentheses, those are used to exclude or not include the endpoints. Okay, remember, if I'm going too fast, don't hesitate to just pause the video and write down what you need to write. Okay, let's describe the set of numbers x that are less than 6 in interval notation. Okay, so to me it helps to imagine this on a number line. So here's what I'm picturing in my head is, okay, real numbers, well, if it doesn't say what kind of numbers, like here, it doesn't say real or integers, always assume it's real numbers unless it's specified otherwise. Okay, so here's 6, and then real numbers less than 6 would be anything along here. So we're not including 6, so we've got an open circle. Okay, there's the set. Now in interval notation, you start at the lowest number included in the set, and you go up to the highest number, and you only list those two numbers. So in interval notation, well, the lowest number here, technically there's not a lowest number. It goes all the way to negative infinity. So that would be what we would write first. Anything from negative infinity to, so we'll put a comma, 6. Now 6 is not included in this set of numbers, so we're going to use a parenthesis on that end. And now technically anytime that you have an infinity or a negative infinity as your other endpoint, you can't include infinity because nothing can ever equal infinity. So you always use a parenthesis if you have infinity on one side. So this describes the set of real numbers between negative infinity and 6. Now let me give you a word of caution here. This looks very, very similar to a coordinate point. Now in this case it's obvious it's not a coordinate point because infinity doesn't make sense. This pen is a little difficult to write with. So it looks similar to a coordinate point, such as, you know, maybe the xy coordinate 3, 2 or something. So you have to know from context whether you're looking at an interval or a coordinate point, an x, y point. So just beware, just because you see two parentheses does not necessarily mean it's a coordinate point. Now this has two different meanings. Okay, but again, what it is the lowest number, comma, the highest number, and then you use parentheses and or brackets to include or exclude the endpoints. So let's do another example here. Let's describe the set of numbers that includes all real numbers except 2 in both interval notation and set builder notation, and we'll draw it on a number line. Okay, so let's start with interval notation. All real numbers less than 2. You know what? Actually, let's start with a number line because this is going to be difficult to picture to make it easier to figure out. So here's 2. I'm going to put that in the middle. So everything except for 2. So we'll have an open circle at 2, but everything else is included in this set. And now I should write, since I'm not putting any tick marks here, I should write infinity and negative infinity here. Okay, everything else is included. Well, so how do we do that in interval notation? Well, the lowest number, we just go from left to right across the number line, and the lowest number is negative infinity. So we'll go from negative infinity to 2. Now I'm not going to include 2, so I'll put a parenthesis, comma, because now there's a second set. The second set goes from 2 all the way up to infinity. Again, I'm not including 2, so I'll put a parenthesis, 2 to infinity. So here is the set in interval notation. In set builder notation, there's a couple ways to do it. You could say the set of all, and then you pick your variable. Again, I'll go with x for consistency, but you can choose any letter you want. So we'll say the set of all x such that, remember you can use the colon or the vertical line, such that, now the easiest way to write it is just to say x does not equal 2. Now I did not actually put here, like I did up here, x is a real number or x is an integer. Because if you leave that off, you assume it's a real number. Okay, so up here, the other way to write this one would have been to say the set of all x such that x is greater than 3 or x is less than or equal to 1. You don't have to put it's a real number because if it's not there, that's what you assume. Okay, so down here, we're talking about real numbers. Therefore, I'm not going to write out x as a real number every single time. So you would just assume, okay, this means x is anything but 2, any other real numbers. Okay, or you could say, another way to do it in set builder notation would be to say the set of all x such that x is less than 2 or x is greater than 2. That also describes the set. So there it is in both interval and set builder notation. And we have it on a number line. Okay. Next, let's look at relations and functions. So that's it for sets right there. So relations. What is a relation? Well, it's a set of ordered pairs. Remember how up here I mentioned coordinate points, like x comma y is 3 comma 2. Going back to that now. So we're no longer talking about sets of simple numbers. We're talking about coordinate points here. A relation is a set of ordered pairs. So an x comma y. Okay, that x, that's considered your input value. The y, or whatever is listed second, is considered your output value. Okay, the set of all the input values, notice that word set, the set of all the input values is called the domain. It may be a familiar word to you. And the set of all the output values, or the y values, that's called the range. So it might help you to write the set of input values, that's your set of x's. Your set of output values, that's your set of y's. So that's your domain and range. So we're going to practice finding domain and range on a couple of examples here. Okay, first example. First class stamp rates all the way from 1900 to 2000. You can see they've dramatically increased. Okay, so we have the year and then the rate. So the year here is going to be considered the x, that's the independent variable or the input. And then if you input the year, this chart will tell you how much a stamp cost in that year. That's considered the y, or the output value. So the set of ordered pairs would be, for example, this. That's an ordered pair. So 1900, comma 2. And you always list ordered pairs in a set of parentheses. Now you just know from context this does not mean the set of numbers between 19 and 100 and 2, which for one doesn't make sense just because 2 is less than 1900. So this would be in the wrong order. But 2, it just doesn't make sense based on the context of the problem. Okay, comma, the next ordered pair would be this one from 1920, 20, comma 2, and then so on. Okay, so there's the set of ordered pairs. Now remember here, the set of input values, or your x's, that's the domain. So the domain here, now it's a set, so we need to use a proper set notation. So I'm going to use the set builder notation and say the set of all x such that, now is this a finite or an infinite set? The domain. The domain are all your x's. So I'm going to underline all the x's here. And the fact that it's possible for me to underline all the x's means that it must be a finite set. That is, it has a countable number of objects in it. 1, 2, 3, 4, 5, 6 objects in the set. So we cannot use interval notation or an inequality to describe this set because it's a finite set of numbers and we are not including all the numbers between 1900 and 1920. We only mean to say exactly 1900, 1920, 1940, so you really just have to explicitly list them out in this case. And the range, that's your set of output values. So we have 2, 3, 4, 15, and 33. Now you might have noticed 2 is actually there twice. You never list it twice in the range, so you would just say, I'm using y because it's for range. So the set of all y such that y equals 2, 3, 4, 15, or 33. So there's no reason to put 2 twice. You only need it there once. So that's domain and range, your input values and your output values. Now there's a special type of relation called a function. A function is a relation in which each x value, or each value in the domain, is assigned exactly one y value. Okay, it's a relation where each x value gets exactly one y value. Okay, not all relations are functions. Some are, some aren't. So let's look at an example. Is this relation a function? It's the relation between shoe size and price. Okay, now here's our x's, 7, 8, and 9. Those are x values. Here's our y's. Now, how many y's does each x get? That's the question. Each x here, 7, 8, and 9, gets one y. When x is 7, the y is 35. That's it. It's not, if your shoe size is 7, the price could be 35 or 30. It's the price is 35. When x is 8, the price is 35. That's one number there. When x is 9, the price is 35. That's one number. So each x does have exactly one y. So this is a function. Example. Determine whether this relation is a function or not. Okay, so we have 1 to 5 is the first coordinate point, then 2 to 6, 3 to 7, -1 to 6, -2 to 5, and 3 to 2. Okay, now remember, a function is one where each x has only one y. So the question is, are there any x's that have more than one y? And if we look, we have our x's are 1, 2, 3, -1, -2, and -3. 3 is here twice. And 3 is only one x value. Just because it's listed twice doesn't mean there's two different 3's. X equals 3 is a single value. And if you look, x equals 3 is assigned y value of 7, and x equals 3 is assigned a y value of 2. So we go from 3 to 7, and we go from 3 to 2. So this is not a function because x equals 3 has two y's. Okay, and then here's a more practical relation. The relation from last name, so that's our x's, to social security number. So are there any last names that have more than one social security number? And of course the answer is yes. Just think of a common last name, maybe Jones or something. Jones is going to have multiple different social security numbers, one for each person with the last name of Jones. Right, so as you can see, this is definitely not a function. Okay, another way to look at it is to look at the graph of the relation. Okay, so here's a relation that has 4 points. When x is -4, y is -2. When x is -2, y is -1. When x is -1, y is -1. And when x is 1, y is 2. So were there any x values that had more than one y? And the answer is no. When x is 4, you have a single y. When x is -2, you have a single y. Same thing when -1 and 1. So this is a function here. That, by the way, is my shorthand notation for function. It's f and then a little superscript underline n. Just means function. This next one, when x is -2, y is -3. When x is 1, y is 2 or 3. And when x is 2, y is -1. This right here means when x is 1, y is 2 or 3. So this is not a function because x equals 1 has two different y's. Okay, and this brings us to the vertical line test. What the vertical line test says is that if a vertical line can be drawn on the graph, so thinking of these up here, so that it intersects a graph more than once, then the graph is not the graph of a function. So what you want to imagine is, say your pen or your pencil, okay? Take a vertical line. Now you have to imagine, because I really can't demonstrate this on screen, I can draw in several vertical lines, okay, but imagine scanning this axis from left to right with a vertical line like your pencil. So put your pencil here like this, okay, and then you move it along. Now right now you're not touching any point, so it's fine, it's still a function. Then we move it down, still not touching anything. Keep moving it, and okay, here we're touching a point, but it's only touching one point at this point in time, so it's still a function. Then we keep going, and then we hit these right here. Now right here it's actually touching 2 points at once. Therefore it fails the vertical line test and it's not a function. So if you, as you move this vertical line across the graph, if you ever touch more than one point at the same time, it's not a function. So because right here we hit 2 points at once with that vertical line, it's not a function. Okay, let's use that same test on each of these. Okay, so try these on your own first. On this first one, if we imagine a vertical line going across, here I'm only touching 1 point, 1 point, 1 point on that blue line, and I'm only ever going to touch 1 point at a time. So that is a function. Again here, I'm only touching 1 point at a time as I move my vertical line across, so that is a function. Here I'm not touching any points, that's okay because these x values are not even in the domain. Now right here when x is 0 I touch exactly 1 point right there, but then after that, anywhere after here we're touching 2 points at once, here and here. So it fails the vertical line test, so that is not a function. And then here not touching anything till we get to here, and all of a sudden we touch infinitely many points all at the same time, so that one's definitely not a function. Okay, so you can see graphically what functions look like and what they do not. Okay, let's look at lines in a little bit more depth. So this right here is a line, that one's a line, and that one is a line. Okay, those three are all lines. This one right here is called a parabola. We'll get to that later in the course. Okay, but for lines, now you should have had a little bit of a math before this class on lines. So what you may have noticed up here is that all of these lines will pass the vertical line test except for vertical lines. But if the line is at least slightly tilted, like this one is slanted to the side, it's going to pass the vertical line test. There's no way the vertical line can touch more than 1 point at a time. So the graph of a linear equation is a line, and a line that is not vertical will pass the vertical line test. So all lines are functions, or rather all linear equations are functions except for vertical lines. Okay, so let's look at some examples. Which of these following ones are linear? Which of the following linear equations are functions? Now we don't have the graph, so it's a little bit harder to see. Okay, now we have to remember is what kind of equation does a vertical line have? Because all the other ones will be functions. So all we need to do is figure out, well, which of these are vertical lines? Okay, vertical lines look like this right here on part D. There's a lot of markings there you'll just have to ignore, but the blue line underneath it all looks about like that. The equation of this line is a simple equation, and if you'll notice, all the x values on the line are 2 in this case, because every x value every point on the line has the same x value. Y can be anything. Y can be -5, -3, 0, whatever, but x has to be 2 for it to be on the line. Therefore, the equation of this line is x equals 2. The equation of any vertical line is x equals a number. So if the vertical line had been over here, maybe at -3, the equation there would have been x equals -3. Okay, so vertical lines have the specific form of the equation x equals a number. Therefore, this one is not a vertical line, so that is a function. This is not a vertical line, that is a function. Same thing here, not a vertical line. This one, x equals -1, that is a vertical line. Therefore, that one is not a function. Okay, and remember another way to think about it is that each y has only one x. So when you look at these equations up here, if you plug in any x value, you're only going to get exactly one y value. Same thing here. If we plugged in x equals 1, for example, we would only get a single y value. 2 plus 1 is 3. We're only going to get one number for y for each x we plug in. Now here there's no place to plug in, but no matter what you try to plug in, you always get the same y value. And you always only get one y value. Y is always just simply 5. Now here, x for each x, actually there's only one x, but y can be anything that goes with that x. So that's why that one x, when x is -1, has infinitely many y's. So what I want to do is solve for y on these equations and use that to determine whether the equation defines y as a function of x. Okay, so on this first one, to solve for y, all we need to do is move the x squared over. So subtracting x squared from both sides, we get y equals 3 minus x squared. And right here, we can tell this is a function, because no matter what x value you plug in, if you plug in any number, you're only going to get a single y value. So for example, if we plugged in, let's just say 2 in for x, any number, you're going to get, in this case, -1, but the point is it's a single value. So that is a function. Now let's look at this one. This is a little bit different. Solving this one for y, first we need to do the same thing, move the x squared over. So we have y squared equals 3 minus x squared. And then to get y by itself, we actually have to take the square root of both sides. And you may or may not have learned this before. We're going to go over this in detail later on in this course. But when you take the square root of a variable, you actually have to put a plus or minus there, because it's possible that variable could be positive or negative and still make it work. So the point is, in this case, y could be the positive or the negative of that square root. So there's actually 2 y's for every x. Let's plug in a number so you can see what I'm referring to. So let's plug in, let's say, x equals 1. No, let's do x equals 2. If we plug in 2, we'd have y equals plus or minus the square root of 3 minus 2. Oh, 2 is a bad choice. Let's go back to 1. We'll just undo that. So let's go back to 1. Sorry about that. Okay. So y is plus or minus the square root of 3 minus 1 squared, or y equals plus or minus the square root of 3 minus 1 squared is 2. So when x is 1, y could be positive or negative radical 2. So there's 2 y's there for that single x value. So this is not a function. So you can tell from looking at the equation, if it's solved for y, you can pretty much tell if it's a function, because if it does not have a plus or minus or anything like that, it's going to be a function. If it does, it's not a function, because there's more than one y for each x. Okay, for things that are functions, you can use this handy notation. It's going to be so handy later on for you. I know for now it's a little confusing, but you'll get used to it. And it is called function notation. Okay, any point on a graph can be written either as a coordinate point or in function notation. So let's look at this. Let's just start by getting a point on the graph. So what are the coordinates of the lowest point on this graph? So here's the lowest point. Remember, we always put x comma y. So 3 comma -4 right there. Those are the coordinates of the lowest point there. And in function notation, the way to write this is to say that f of 3 equals -4. So if this is the function f of x, that's read f of x, not f times x. F is the function name. Okay, that's the function name there. We're calling this one f, but the function name can really be anything. Now this means of 3. That's how that's read. Of 3, meaning when x is 3, the y value equals -4. That's how you read this. Okay. So in function notation, let's look at a different point. One of the x-intercepts. Now x-intercepts are where the function crosses the x-axis. So that happens in 2 places on this graph. One is right here at -3. The other is right there at 5. So let's look at this -3 one. The coordinates of this point are -3 comma 0. So in function notation, the x goes in with that f. So you would say f of negative 3 equals 0. So there that is in function notation. The other x-intercept over here is this one, whose coordinate point is 5, 0. So you would say f of 5 equals 0. Okay, so if you have a function f such that f of 3 equals negative 1, which is not true up here. Okay, we're no longer looking at this graph, different function. But if we have some function f such that f of 3 equals negative 1, this means when x is 3, f of x is equal to negative 1. So f of x is really just a different way of writing y. That's really all it is. Now the advantage to using f of x is you can see the input value there. You can see, oh, this is y is negative 1 when x is 3, rather than just knowing y is negative 1. Okay, so in this case, if x is 3, f of x is negative 1, which means the point 3, comma, negative 1 is a point that graph passes through. Okay, another way to state this is to say that both f of x equals, say, 5x plus 3, or whatever the function definition is, and y equals 5x plus 3 are actually the same thing. Because like I said, y and f of x are equivalent. They're just two different ways of writing the same thing. So both of these are the set of ordered pairs x, comma, y. But y is actually defined as 5x plus 3. So you could look at this as all the points as that are defined by x, comma, 5x plus 3. So this describes every coordinate point on this graph f of x. You would just plug in different x's to get more specific values. So for example, we could say if x is 1, then that y value would be 5 times 1, which is 5, plus 3, or 8. Or if x was, say, 0, you'd have 5 times 0, or 0, plus 3 is 3. So you just plug in different x values here, but this describes every ordered pair, x, comma, 5x plus 3, and both of those are defined by the f of x equals 5x plus 3 or y equals 5x plus 3. They mean the same thing. Okay, so the handy thing, like I said, is you can see the x value that's being input. So let's use function notation to find a few y values. Okay, so given g of x equals x squared plus 5, let's find these following y values. Let's find g of 2. G of 2 means replace this x right here by 2. Okay, whatever your function definition is up here, whatever's here, you replace it by what's in the parentheses here. So in this case, we're going to replace this x by 2. So we would have 2 squared plus 5, or 9. G of negative 5 would be to put a negative 5 in for x. Now this is actually not correct, what I'm writing here. This is wrong. Okay, the reason why is because of order of operations. You have to put those parentheses around the negative 5 because it's negative 5 all squared. In other words, the negative gets squared as well as the 5. So negative 5 times negative 5 is positive 25, or you get 30. Now what would be, let me show you the difference. So this is the wrong way to do it. Would be to say g of negative 5 equals negative 5 squared plus 5. Now you remember order of operations, PEMDAS. Please excuse my dear Aunt Sally. So what this is says parentheses, exponents, multiplication, division, addition, subtraction. And this is the order in which you apply things. The very first thing is parentheses. We don't have any parentheses here. Next, you apply exponents. So we would apply that 5, but only directly to what that exponent is written to, which is the 5. So we'd have negative 5 squared is 25. But that negative stays out front because we have not yet multiplied, multiplication is next, by the negative 1. Okay, so in this case you would actually get negative 20, which is wrong. So you have to have those parentheses there. Be very careful about that. Okay, and I will count off. Even if you get the right answer, if your parentheses are not here, you'll definitely get counted off because you've got to get in the habit of writing what you mean, which is very, very important. When you get to more complex problems and you're writing a whole line, maybe your math problem might take a whole sheet of paper all the way across to write a single line of work. by the time you restart working on the next line, you're going to forget whether or not you intended to put parentheses and we're just too lazy to write them. So if you mean to write parentheses, write them. Okay, next let's plug in 0. So just find one more. G of 0 would be 0 squared plus 5 or just 5. So that's how you find y values given an x. And like I said, the nice thing here is that you can see the input. So if I had just written y equals 5, well, y equals 5 when x is what? But using function notation, it indicates y is 5 when x is 0. So it's very handy. Okay, let's do this going in a backwards order. Let's find the x value such that f of x equals 5. For this function, f of x equals 3x minus 10. I want to find the x. Okay, I'm not finding the y value, I'm finding the x, such that f of x equals 5. So I'm going to replace f of x by 5. In other words, this means where y equals 5, in other words. So I'm replacing f of x by 5, and then we can solve for x. So we can add 10 to both sides. 5 plus 10 is 15. And we can then divide both sides by 3. 15 divided by 3 is 5. So we would get x equals 5 when y is 5. Okay, so one way to think about a function is to think of it sort of as a black box. Okay, you input a value here for x and you get another output value for y. So you input your x, you put it into this function. The function does something to it, changes it most likely, and outputs your f of x or your y. Okay, that's just one way to think of it. So what this function up here does in the inside of the box is it multiplies x by 3 and then subtracts 10. So for example, this could be, I'm not going to leave this here, but this could be 3x minus 10. Right? It changes it and then it gives you the output. But the f does something to it. So you have your input, what the function does, and then the output. Okay, let's do a couple more with graphs. A few more examples. So here's a graph of a function f right here. And over here on the right is the graph of a function titled g. So this one has a different function name. F, g, and h are very, very common function names, but it could be anything. So let's find f of 2. Remember, this means x equals 2. So you're finding, well, what is f of 2 is the y value when x is 2. If it says f of something, that's referring to a y value. So we go up here to where x equals 2, here's x equals 2, go up to the function, and we get y equals 1. Therefore, f of 2 equals 1. G of 3, so we're now looking at the graph on the right. G of 3 is when x is 3, what is y? So you go to where x is 3, here's x equals 3. Actually, y is 0 at this point. Y is not positive or negative. So therefore, g of 3 equals 0. Okay, let's find all the x values such that f of x equals 2. In other words, where does y equals 2? Where does the function equal to? So we're looking at the y values now. Well, here's where y equals 2 right here. It's highlighted in red. So we say, okay, what are the x values? It says find all x values where f of x equals 2. So one of them is already marked. You can go over here to the right. You hit the function and you go down, and it looks like when x is 4, f of x equals 2. In other words, f of 4 equals 2. Okay, and that's one of them. But if you look, there's also another answer over here. When x is negative 4, y is also 2. So when x is 4 or negative 4, f of x equals 2. So I'm going to write it in its other notation here would be to say f of 4 and f of negative 4 both equal 2. Now this is a run-on inequality, but that's okay because it's what it says is actually accurate. F of 4 does equal f of negative 4, and they both are equal to 2. Okay, and then let's find the x values such that g of x equals 3. So you're kind of imagining, as you can see from here, a horizontal line. Okay, so when g of x is 3, here's 3. Let's draw in a horizontal line. That way we get all the x values, not just a couple of them. So it looks like x could be right here. So x could be negative 3. Or right here we intersect the function. So when x is 5, g of 5 is also 3. So when x is negative 3 or 5, g of x is equal to 3. Okay, so let's look at some applied problems to make sure that you can read the functions from graphs and work with function notation. Then we're going to do a little bit more with domain and range after that, and then we'll be done with this section. Okay, so first, let's look at this. Here's a graph of pharmaceutical research and development expenditures over years. So this is dollars on the y-axis, years on the x-axis. Let's approximate the money spent in 2005. So the idea is you have to figure out, well, which axis is that on? And in this example, it's fairly easy because 2005 is only on one of the axes, right? It's got to be an x value. So approximate the other way to figure it out is it says to approximate the money spent. Well, money spent would be dollars, which is here on the y-axis. So in 2005, we come up. Here we go. It looks like it hits right about at that white line. Pretty close to it. So about 40. Now the answer is not $40. Okay, you have to look at the units here. This says dollars in billions. So you could say 40 billion, or you could actually write it out 40 billion. Let's see, this is your thousands, so there's your millions, so there's our billions. That works. Okay, so that's just reading the graph. Now let's look at it in function notation. So what can be done if you have a graph like this, because this looks pretty linear, but it's not exactly a straight line. So what you can do is you can actually approximate the function by a straight line using a method called least squares. If you ever take a statistics class, you'll definitely learn that. That's one of the biggest things they do in statistics, is do least squares approximations to get lines that approximate data that's not perfectly on a straight line, but that's close. Okay, and what they did is they found that in this case, the equation of that line is given by f of x equals 2.602 times x minus 5178. So that's the equation of that line. Let's use that to approximate the money spent in 2013. Okay, so what you'll notice here is that 2013 is not on this x-axis. That's actually 5 years past where this ends. Okay, so one thing you do have to be aware of is that in the real world, you don't actually know that this is going to continue going up in a straight line. Okay, it's possible pharmaceutical research might change and it might start going up exponentially, or it might drop. Okay, but the assumption is if it continues going up in a straight line or growing linearly, then we could approximate the money that would be spent in 2013. So what is the x value in 2013? Well, years is our x-axis, so x would equal 2013. That's what we're looking at. What is y, or what is the money spent? So what is the y in 2013? Well, that would be f of 2013, which is 2.602 times 2013 minus 5178. Grab your calculator and see what you get for that. And it looks like I get 59.826. So therefore, the answer would be that many billion. So about 59.826 billion. Now it says to approximate. This is really close to 60 billion. So I would say, so approximately, and that's shorthand for approximately, 60 billion would actually be my final answer. That's how I would round there. Okay, so function notation can be used for applied problems or more theoretical problems. Okay, next let's look at finding domain and range of functions. Just given the equation, how do you find domain and range if all you're given is the equation? And the ones we did before, we were given either a list of numbers, a table of data values, or a graph, so we could read it from the graph. But what if you're just given the equation? Well, the easiest way is to find the numbers that are not in the domain. Okay, we're just going to find domain first, and then everything else is in your domain. So for example, with this function, the question is, what numbers can you not plug in? What numbers x can you not plug in? Because remember, domain are your x values or your input values. Well, this is a fraction, 1 divided by x. Now there's only one number that we cannot divide by. We can divide by positive numbers, negative numbers, fractions, decimals. The only number that we cannot divide by is 0. So 0 is not in the domain. So x equals 0 is not in the domain, which means all other real numbers actually are in the domain. So everything except 0 is in the domain. So if you're imagining it on a number line, we had one like this earlier that excluded 2. Well, here's 0, so everything but 0. So all these x values are in the domain. We just can't plug in 0 because 1 divided by 0 is undefined. So your domain, in a more formal notation, would be the set of all x such that, now the easiest way to describe it is just to say such that x does not equal 0. That implies that x is a real number because we didn't specify, and it implies that x can be anything else. In interval notation, you would start from left, you go from left to right. So you start down here, which is negative infinity. So in interval notation, it would be from negative infinity to 0. We're not including 0, so parenthesis, comma, from 0 to infinity, everything after 0. So that would be all real numbers except 0. Okay, now a common mistake and what people sometimes do, let me show you this mistake I see a lot, is sometimes students will do this. They'd say the domain is from negative infinity to negative 1 and from 1 to infinity. What's wrong with this is that you're not including all those decimal numbers between negative 1 and 0 and between 0 and 1. You know, 0.5 is in the domain because you can plug in 0.5, right? F of 0.5 is 1 divided by 0.5 and you get 0.5 and you get a number, you get 2. Okay, so that is in the domain. However, this does not include 0.5, so you've forgotten some decimal numbers. So you have to remember x is a real number, so it can be fractions or decimals as well. All right, let's look at another example. F of x equals 2x minus 4. Are there any x values that for any reason you cannot plug into this? And you can think about it all day, but no matter what you plug in for x, you can always multiply it by 2 and subtract 4. So you can plug in any x, well, any real number x to this. So therefore the domain, and oftentimes you'll see capital D for domain, shouldn't write that. So the domain, or capital D for domain, is all real numbers. You can either write out all real numbers, or you could write it in set notation. You would just have to say the set of all x such that, since there's nothing really to say, you would have to say x is a real number. Or you could say all the way from negative infinity to infinity in interval notation. So all of these are correct ways to state the domain. And while we're talking about real numbers, let me show you shorthand for all real numbers. If you do a double bar, capital R, that is shorthand for the set of all real numbers. So you might see that somewhere. It's a double bar, real R. If you're typing on a computer, it's common to use bold capital R for that instead. Now let's do one more example here. Make sure you try this one on your own first. Find the domain of g of x equals 1 over x squared. So again, are there any x numbers that for any reason you cannot plug into this function? And this is real similar to the first one we did up here. What value of x is going to make that denominator 0? That's the question. What value of x will make the denominator, or x squared, equal to 0? Because that number is not going to be in the domain. Well, solving this equation for x, you take the square root of both sides. You get x equals plus or minus 0. Well, positive 0 and negative 0 are the same. So you get x equals 0. So if x is 0, this is not defined. So this one actually has the same domain as this first one. The domain would be the set of all x such that x does not equal 0. Okay, And let's do one last example here. And now in this one, we're going to find both the domain and the range. I did not find the range in these examples because you have to know about what the graphs of these look like, which we'll get to later in the course. And when we do, maybe we'll find range then on some of these. But for now, we're just finding domains of the equations. But if you're given the graph, it's much, much easier to find range. But let's start with domain on this first one. Domain. So we're going to use capital D and abbreviate. Okay, remember domain is the set of input values. Now it looks like nothing outside of -4 or less than -4 and nothing greater than +6 is in the domain. So the domain would be simply numbers from -4 to 6, and we have a closed circle here on both ends. So we're including -4 because when y is -4, or when x is -4, y is defined as 3. And when x is 6, y is defined as -2. So we include those. So in interval notation, it goes from -4 up to 6. And I'm including the endpoint, so I'm using those brackets finally. And I just usually go for the simplest way to write it, so I'm just going to stick with from 4 to 6 in interval notation for that domain. And for the range, let's use the capital R to abbreviate range. That's the y values. So you're looking at the lowest and highest y value on the graph. So what I'm doing is I'm sort of scanning with my eyes, imagining a horizontal line, and then I move it up. So far I haven't hit any y values in the graph. Haven't hit any. And then, okay, here I hit my first y value. So the lowest y value is -2. It is included because of that closed circle there. So the range goes from -2 up to, okay, all of these values are in the range. We have a y, we have a y, we have a y. The last y value here is 3. That's the largest y value. So the range goes from -2 up to 3. And we include that because we do have a closed circle there. So there's domain and range on the first one. Now try it on your own on this second one. Okay, for range, the question is, are there any x's not in the domain? Or in other words, what x's are in the domain? Now this one has a little arrow, which indicates that this thing keeps going forever, which means all these x's all the way out to -infinity will always have a y if that goes down forever. Same thing in this direction. All of those x's will always have a y if this is going down forever. So the domain actually goes from -infinity all the way to infinity. And the range, that's the y. So we're scanning, remember, the y-axis from low to high. So we start at the lowest number, end at the largest number. Now the lowest number, if this goes down forever, the lowest number would be -infinity because that just goes down forever. And then I'm scanning the y-axis. Okay, we have values, we have values, we have y values all the way up to y equals 3. That's my last y value there. It is included because there's a closed circle there, so we use a bracket. All right, so there we are for domain and range. That's it for sets and functions. So there's lots of homework for you to practice on these, and then we're going to use set notation and function notation in all of the upcoming sections for the rest of this course. So hopefully that was partially reviewed but answered any questions or concerns that you had about functions and sets. So I will see you next time for the start of Chapter 7 with 7.1.